Hello everyone, welcome to my presentation. My name is Samira Soleimani. I'm a senior data scientist at CGI. Today I'm going to talk about optimization in vaccine management problem. What is optimization? Optimization is nothing but selecting some inputs that will result in the best possible outputs. In our everyday life, we are facing with different problems that can be solved using optimization techniques. Whenever we want to optimize something, like for a stock market, day traders usually try to maximize their profit by buying or selling a specific stock in a specific time. Or in another example, civil engineers, while building foundation of a structure of a building, they are trying to maximize the strength of that foundation. However, they want to minimize the cost and amount of materials they want to use to build that foundation. In this study, I'm going to talk about the difference between single and multi-objective optimization, and then I'm going to talk about how we can set up an optimization problem, and based on what we've learned, we will work together to see how we can solve a vaccine management problem using optimization techniques. So what's the difference between single and multi-objective optimization? As you can tell by name, single objective optimization only tries to satisfy one objective that the problem has. Like for stock market, the only objective that we will have is maximizing the profit. So there would be only one solution, one specific solution to solve this problem. However, whenever we have multi-objective optimization, we have more than one objective. Like for designing the wings of a jet, we have two objectives. One of them is minimizing the weight, of the wing. However, the other one is maximizing the modal response of the wing. So these two objectives are somehow against each other. So we don't really have one specific solutions. We will get a paret of optimal solutions, and all the points on this line can be considered as an optimal solution to solve the problem. All right. To set up an optimization problem, we need to define three things: objective function, constraint, and solver. Objective function is a mathematical equation behind an objective function, a mathematical equation that reflects objective function in a mathematical way. So we can use math techniques to obtain the global minimum or maximum based on the nature of the problem. We can use either line fitting or curve fitting, on the data set, and then create that specific mathematical equation behind our objective function. Another thing is constraint. All the variables in our data set may have some specific constraint that we need to consider them before solving the problem. And finally, we need to define a solver, which would be either Lagrange gradient descent or meta-heuristic algorithm based on the complexity of objective function. Like for previous example, in a stock market, if we just fit a curved line on the points that we had, and we will get this function as an objective function, then considering the constraint and using gradient descent, we can easily find the best solution for maximum profit. So let's work together to see how we can solve vaccine management problem using optimization techniques. The problem that we have here, we have like more than 300 vaccination centers that we want to, cluster them into different neighborhoods and efficiently order vaccine for each of these neighborhoods in a way that maximizes the administered doses of vaccine, however, minimizes the shortfalls or surpluses. So we have two objectives: maximizing the administered doses, however, minimizing the shortfall or surpluses. So these two objectives are somehow against each other. The variables that we have like 4 different variables, and we want to predict the optimal values for each variable for every neighborhood that we have. Now it's time to set up our optimization problem. We need to define 3 things: objective functions, constraint, and also solver. For objective function, first thing was we have to cluster all the points into different neighborhoods. We use both k-means and KNN techniques to put all the vaccination centers into different neighborhoods, and then we need to find a mathematical equation behind our two objective function, which was maximizing vaccine administered F2 and also minimizing vaccine shortfalls or surpluses. In order to find F1 or minimizing vaccine shortfall or surpluses, we used line fitting and also curve fitting to find a relationship between the rest of three variables with the target variable, which is vaccine shortfalls or surpluses. For constraint, we used side constraint, and then for solver, based on the complexity of the problem that we have, we use NSPSO, that I will go through that in the next slides. In order to write the objective function that minimizes the vaccine shortfalls or surpluses for each cluster of neighborhood, we had to compare both curve fitting and also line fitting results together to pick the best fitted line or curve and use that line as an objective function. Like for line fitting, we have our target variable as vaccine shortfall or surpluses, and we have to use the three other variables that we have in the data set in order to find a line, and then using this line we can use we can solve our optimization problem by considering this as an objective function. So in order to find out which curve or line would be considered as best fitted curve line, we compare their R-square values. The higher the R-square, the better. Like for this specific cluster, this line would be considered as the best fitted line, so we will pick this one as the objective function to minimize vaccine shortfalls or surpluses in this study. The last step of setting up an optimization problem is selecting a solver. A solver would be defined based on the complexity of objective functions. We have three different solvers: Lagrange, gradient descent, and also meta-heuristic algorithm. In this study, since we have a curve with a sinus term in it, we have to define a meta-heuristic algorithm which is working for a very complex objective functions. One of the meta-heuristic algorithms are multi-objective particle swarm optimization. This algorithm not only considers each population's entire best known position, but it also considers every particle's own best known positions, which help us to make sure that we are searching for the global minimum of an objective function, not finding the local minimum of that specific function. After having everything set up like objective functions, constraint, and solver, we can use PyGMO package in Python to create and assign our population, and then solve the problem and find the global minimum for all the objective functions. If you may remember, since we have more than one objective function, which are minimizing shortfall and surpluses and also maximizing number of administered vaccine, so we don't really have one specific solution or one specific point as the final solution of the problem, but we have a palette of optimal ones. You can see here the line in the front in very dark black. We can consider that as Pareto optimal, and all the points on that can be considered as optimal solution. But using PyGMO, we created this population. These results are without applying algorithm, but after applying NSPSO algorithm, you can see the Pareto optimal, how this Pareto optimal moves here. Like for minimizing shortfall and surpluses, you can see this point is around 40 something, but after applying NSPSO algorithm, you can see this number is around 10 or 20. So this is how our final result looks like. So for every variables, you can see that we have an optimal values based on either line or curve fitting for objective functions, and also based on k-means or KNN for clustering neighborhoods. So for every neighborhood, we have a specific optimal values that we can use in order to optimize our vaccine distribution problem. Thank you very much for listening. If you have any questions, feel free to reach out to me.